Okay, hello everyone. We are now seeing light at the end of the tunnel. We're going on to module 5. It's quite a big module, so we have to move it along a little bit. If we don't finish, module 6 is short, so that'll be all right. So we'll finish both of them by next week. All right then. AC machines. So we're going to talk tonight about synchronous machines. That means an alternator, and we're going to look at these in depth. The motors is just basically in N5. We just do a bit of theory on the synchronous motors, okay? So I'm going to leave that to you guys to read up. Just read up on the theory of it, okay? Otherwise, we'll never. This is a big chunk of work. This topic, this module. But we'll also do three-phase induction motors in depth as well. So I want you to self-study this one, please. It is otherwise we're just going to go through slides, and that's not going to help anybody. I'd rather show you some of the calculations. All right. What is a synchronous machine? Okay, it's an AC machine that you can either run as a generator, and we call it an alternator, right? When you providing it with mechanical input power, or you can run it as a motor if you provide it with electrical energy. Hey, so if synchronous motors are run, or alternators as well, they run the shaft speed, the actual rotor speed, is the same as the magnetic, the rotating magnetic field that rotates in the middle of the in this machine. So with small alternators, these are not synchronous alternators, these small ones. We used to having this magnetic field with these stationary poles here on the outside. This would be, say, these poles, like a DC machine, hey? Let's do it like that. Where you had poles making magnetic flux. And then the rotating stuff is carrying the heavy current, hey? So if this was a generator, then the current would be coming out here from this rotating part. But that's okay if it's very small. With the large alternators, it's not going to work. So on your rotor, there's the two parts of this thing, huh? The stator assembly, or the stator, and this rotor on the inside. Rotor for rotating, stationary, it means stator. All right, so you have windings on the rotor, and then you put, using a DC voltage source, you pass this excitation current or field current through that, and then see the green dotted lines make a flux, magnetic flux. Now, of course, you turn this with a prime mover, whether it's a steam turbine or whatever it is, then this flux is turning round and round at the same speed as the rotor speed. So that's very important, okay? The magnetic flux speed is the same speed as the rotor speed. Then this magnetic flux cuts across these three-phase windings over here, and what happens then? It generates or induces EMF. There's your phase EMF. Okay, P. All right. So these three coils, that's just a representation. It actually looks like that, those three coils. So you have a stator assembly with lots of these slots in it. So this is specific terminology, hey? Slots. These are called slots. And you can see that these coils, yes, that is called a coil. Now, these coils are wound in these specific slots. And because they're three separate coils, each one of them has a single phase. Hence, this is how we generate three-phase power in three different cores. Eh? So that could be, for instance, red, Y, and B. So we know with Faraday's law, with that rotating magnetic field, then we're going to get this EMF in the armature or the stator windings. And then as soon as you connect a load to these stator windings, then you're going to get output current. Now the EMF per phase, so here we have an E per phase. Let's take one of the phases, is 4 times the frequency of this output waveform. So this will be at 50 hertz typically, times the number of turns per phase. Remember those coils? Well, if you have one, this is one turn. This is one turn. But each coil has many turns, eh? So this thing goes like that. Okay, I'm not the best artist, okay? So many turns equal one coil. So the turns per phase would just be one of those 360-degree turns. And then you have the form factor here, which is 1,111. That's for a sine wave. And in 5, you only use 1,111. We don't change that till N6. And then I'm going to show you what these two constants are on the next slide. So because they're synchronous machines, they synchronize with the grid. And we have that little formula. If we are generating, say, a 50 hertz waveform, then would be the synchronous speed, that's RPM of the magnetic field, times the pole pairs over 60. So in this case, P would equal 3 pairs. Don't make that mistake and use 6, eh? All right. So there's a definite relation there between, use this one, between the frequency, the output frequency, and the number of poles and the speed. So those are all very interlinked or dependent on each other. So to find the synchronous speed, then you just rearrange that little formula, and it's 60 times your output waveform frequency divided by the number of poles, pole pairs. Okay, now I just got to show you that there's a difference that we use in the measurement of mechanical and electrical degrees. So an angle, let's take this 4-pole motor. All right, so for instance, this one, we can see north, south, okay, like that. You've got 4 poles. Now we can see, obviously, from the drawing that the mechanical degrees between 2 adjacent poles is 90 degrees. Hey, that's pretty clear. But at the same time, electrically, between a north and a south pole, it is always 180 degrees electrically. North and south, 180 degrees. So that is 90 degrees mechanical and 180 degrees electrical. So you can try this out with any of these other examples, but the bottom line is that the electrical degrees is a mechanical degrees times the number of pole pairs. So you can see here, say between 2 adjacent poles is 90 degrees mechanically. How many pole pairs are there? 2. Yep, then 180 degrees. We know already that it's 180 degrees electrically because it's between north and south. Okay, and you can apply it to any of these. You can try it out. All right, so now remember in that we had those 2 constants at the end of our EMF equation, eh? E per phase. What did we have? Okay, you had 4 F pi turns per phase, form factor. Then you had 2 K P K D. these two at the end. Right, what is Kp? I'll show you now. It's called the pitch factor. If you have full pitch coils, so if you've got north and south, now the pole pitch, the angle between adjacent poles here, happen to be, in this example, 90 degrees mechanically. Now let's say that your one of those coils, just take one turn like that. Let's say that we put it in that slot there, make a cross there, and it comes back. So that's that one with the cross, and then the dot, is this one here coming back. All right. Then you can see that the coil pitch, the angle there is also 90 degrees. So they're both 90 degrees. So when the coil pitch equals the pole pitch, we say they are full pitch coils. Then our multiplying factor over here, Kp equals 1. But they're not always. We deliberately make them short pitched. Okay. You get short pitch coils. We do that to reduce harmonics, which are dangerous things in power systems, to reduce the harmonics in the output sine waveform. So now you see here, now we pitch them like this. Then the other side of the coil, for example, is over here. So it's not under the, you see, it's not under the adjacent pole anymore. It's short pitch. So it looks like this. There are the poles, north and south. The one side we put under the north pole. If it was full pitched, it would do that, hey? But now we've short pitched it by a few slots. So there could be a few slots here. So now we put this side of the coil in. We short pitched it. We've reduced that angle. All right. So we've reduced it by this chording angle. So we do it to reduce harmonics. But the thing is that when we do that, we lose a little bit of the EMF. So we have to put a multiplier in here that tells us how much EMF we can. So it'll always be a fraction, 0.95 or something like that. All right. So then, once we know what this angle is, okay, there's the Kp equal 1. It's full pitch. But now here, let's take one example here. If it was here, and now the other side of the coil is there. Now, we say the coil spans 130 degrees electrically. But we know always between north and south is 180. But now our coil pitch is only 130. So this little angle over here, we short by 50 degrees. So we take that 50 degrees and we plug it in here. So this would be cosine 50 over 2. And then we'd work out what Kp is for that one. They can word it differently. Coil span, 3/4 of pole pitch, for instance. Then you're left with 1/4 of 180 is 45, etc., etc. You can go through these. But you get that angle, divide by 2 and find the cosine, and then you've got Kp. Kd is the distribution factor. You also, when you distribute let's say you had a 3-turn coil, but you don't put all 3 turns, all 3 conductors like that. What happened to this? Let me just see something. Okay, that's fine. All right. So the 3 conductors on the one side of the coil and the 3 conductors on the other side of the coil. If it was a concentrated winding, then all 3 of these would be in one slot and all 3 of these would be in another slot. So that would be a concentrated winding. But if we have a distributed winding, we put these 3 in different slots. and that helps us with heat distribution in the armature, and also improves the sine waveform. But we also, by distributing it, we lose a little bit of EMF again. So KD is the EMF with the distributed winding over the EMF with the concentrated winding. So it gives us a multiplying factor that we can multiply EMF equation by to cater for the loss of EMF. So that's fine. So we can do this, or we can write this expression for the EMF of the alternator in two ways. Okay. So there's one thing that I didn't explain yet. So this is a 3-turn coil. So it's a one coil. It's got 3 turns, but each side of one turn, if you break so this side and that side, these we refer to as conductors. So obviously you have 2 conductors equal 1 turn, and many turns make 1 coil. So try and use this one, okay? I've made a copy of this comes from your formula sheet. But this one, so it doesn't confuse you, you can see it doesn't have KF in it. Well, we know that for N5, okay, your KF is going to be 1,111. So what I do, I don't use the one with this 4 and the number of turns, because I know the number of conductors is twice the number of turns. So I use Z, which is the number of conductors per phase, and I make this 2. I want you to keep this KF in, because in 6 they might change that KF, and then you're not used to it. But if you see that KF is 1,111, you see the one, this is from the formula sheet. They don't put it in here, they incorporate it. 2 times 1,111 is that. So I don't like that. I use this full general equation, okay? So you see why that stator winding looks like it does. Hey, it's got all of these coils. You take one phase, the blue. You see, it'll do that, then it'll have another one there, and then it'll have another one there, and then let's say that's your blue phase. That's why there's so many coils on there. It's the more conductors you have, they're all in series, it builds up this total EMF or terminal voltage on open circuit. Okay, so now if you've got a 3-phase star connected alternator, so your N is RPM, required to generate a line voltage of 460, even if they just say generator voltage. Default, when they give you this voltage, is always line, even if they don't tell you. Unless they tell you it's a phase voltage, well, then they're not going to, okay? But sometimes they don't say line, but it's default line. Okay, F is 60 hertz. So the voltage on open circuit, in other words, your EMF. All right, stator has, now you have to watch out with these units. The stator has 2 slots per pole per phase, 2 slots per pole per phase, okay? And 4 conductors in every slot. So what is the number of poles? When you have to work out frequency or number of poles or something like that, or even the synchronous speed, you always use this little frequency formula, okay? So don't forget, when you work out P, when you work out P, it's going to give you pairs. So answer the question. Don't just leave it like that. Give them the number of poles. Otherwise, you'll lose a mark for that. So the useful flux per pole is, okay, that's, what is that? it's a flux symbol. So they're never going to get you to calculate KD in N5, only in N6. So they'll always give you KD. They haven't given us a pitch factor. So if they say full pitch coils, in full pitch coils, no, they haven't given us anything, Or if they leave it out. If they say full pitch coils, or if they leave it out, KP equal 1. All right. So we're going to use our EMF equation. E phase equals to frequency times the flux per pole, number of conductors per phase, KF, KP, KD. Yes. Yeah, it's got a mouthful, So the number, you've got this 2 slots per pole per phase. But let me just take a step back. How do we start finding out what this thing is? So we have to find this. So what do we have? Okay, we've got the E. Okay, we have to modify it to get the phase value, but we've got it. We've got the frequency. KF, we know what that is, 1,111. KP, yes, it's going to be 1, and they give us KD. So in order to get this, we need to calculate the number of conductors per phase. Well, we know that we get 4 conductors in every slot. So we better work out the number of slots, say. So the number of slots per phase, so now use the units to your advantage. So if I multiply this 2 here by the number of poles, I cancel that, So the number of slots per phase is 2 times 8 poles is 16 slots. So the number of conductors per phase, that's slots per phase. All right. Then the number of conductors per phase, I'll just have, because I know there are 4 conductors in every slot. 64 conductors. So this is my ZP. Always, in this EMF equation, phase. It's star connected. VL over root 3 is this number here. Okay, I don't know why I wrote it like that. I should have written KF over here. Okay, so I put all of that in, and I make this the subject of the formula, and then I get 32.25 milliwebers. And then sometimes they get you to work out the EMF, or sometimes the flux, They just mix it up a little bit. But it's basically the same calculation. All right, now what about with alternators? You're unlikely in a plant to get your plant reliant on just one alternator. If it breaks or you have to service it, then your plant doesn't have any power. That's not good business. So what we do, I'm just showing the stators of the alternator. We're not showing the rotor or anything. So these are just the stators, which are now connected onto buzz bars. So what you do, you connect how many of the alternators you have onto the 3-phase buzz bars, and then this goes to your plant or your factory or whatever it is, and then you feed off that to all your different consumers. All right. So now let's say we've got alternator A running already. Then we synchronize alternator B in phase with it. It must have the same frequency. It must have the same phase difference. Otherwise, there's a problem. So is there any EMF? No, there's no EMF. In this case, there's no EMF difference between the two. All right. So if this was EMF, the voltage across this phase, So we call that EPA. Let's call this EMF EPB. All right. So if we're standing over here at the buzz bars, these things must be in phase with each other. Otherwise, there's a big problem. Now, but if you're standing at one of the alternators, you can think of it like that. because this one's putting current onto these bus bars, and this one as well. If you're standing over here, it would appear that this EPB is 180 degrees out of phase to EPA. All right, or to alternator A. Now, so we represent that EPA by a phasor, and then your EPB by another phasor. They're equal magnitudes, but they're 180 degrees out of phase with each other. So if you add those two together, you get zero. So there's no voltage difference which would drive any current circulating between these two alternators. Then it's perfect. Now, if we say on the one alternator, let's say B, let's say we just tap off on the input power, that is the prime mover, in other words, that is driving alternator B. So less power is going into alternator B, basically. All right? And what happens to this vector or phasor? It falls back by this angle, alpha, the load angle. So now you have EPA like that, but now EPB isn't horizontal anymore. Now you have EPB at an angle like that. Now, if you add EPA and EPB in this case, now you do get a resultant voltage between them. So you haven't changed the magnitude. So this magnitude is the same as this magnitude. Just by changing the angle of that phasor, you get a resultant voltage between the two alternators. So this angle is, we make that our reference, 0, and then this angle will be 180 minus alpha. So if we add that, we get this resultant. We get the resultant voltage between these two alternators. Okay, so then what happens if you look at the drawing, the three-phase one there, for instance. Now that those two alternators are connected onto the bus bars, but what will happen now is you'll get this current circulating between alternator A and B. Because, why? Because you have a resultant voltage between the two of them. And notice that the current circulates through the impedance, the phase impedance of A, and the phase impedance of B. So the current there, the circulating current, and you could also call it synchronizing current, is EPR over ZP total. The ZP total is ZA plus ZB. So it's an impedance of both machines together. Normally they're the same. Right. So, okay, let's have a look how we use that. So there are a couple of things we have to calculate here. Circulating current. Then we also have to the common voltage between the two, because now they're both connected onto the same bus bars. So what is that terminal voltage going to be? Well, that terminal voltage per phase is EPA minus half EPR, the resultant, not EPB. So then we can work out the terminal voltage or the bus bar voltage. And then one more thing we have to calculate, the synchronizing power. We worked out the synchronizing current. That is the current that is going to flow from the affected or alternator to the unaffected one. Why does it flow? Because it's drawing power from alternator A. Otherwise, if it doesn't, because remember we dropped the power input on B, so it will drop out of synchronization. So it's pulling current from B to keep it from A in order to keep B synchronized. Okay. So the power is √3 times the line voltage of the terminal voltage. So when you get this, then convert to line. And then that this thing here is that line voltage. The current we've already calculated, and then this phi is the angle between this voltage and this current. I'll show you how we get that now in a minute. All right. Got a lot of stuff, eh? So now we've got two similar three-phase star-connected alternators in parallel. Supply power to common busbar system, machines, blah, blah, blah. Give an open circuit voltage, EMF, of 2.2 kV and 2 kV. You see, they didn't say line voltage. It is line voltage because they didn't say. If they say phase voltage, be careful, eh? Sometimes they tell you it's already a phase voltage. Now, don't go and convert it again and divide it by √3. And funny enough, we were doing this at the full time today. And people didn't see this is a three-phase, right? But you also get question. I gave them a question on a single-phase alternator. And everybody merrily went and started calculating on three-phase because that's the example I'd shown them. Read the questions carefully. Don't speed read these questions. So you can get single-phase calcs as well, eh? Be careful of that. So the impedance of each machine is given, and the phase displacement is 25 degrees electrically. There we go. So now what is this one going to be? It's going to be 180 minus 25. Hey, so this will be 155 degrees. So the current circulating between the machines, so it'll be there. You best work these out separately before. Don't be lazy like me, yeah? All right? So work those phase voltages out separately. Then you can see this one's at 0 degrees. This one's at 155 degrees. This one is the reference at 0 degrees. There we go, EPR. Then, once you've got this resultant voltage, all you do is divide it by 2 times the impedance. So it's this magnitude, 2 times that. And we know the, okay, I didn't do that. So I've converted this to polar, eh? 3,86 angle 80,29 degrees, eh? Ohms. Then I only multiply the magnitude by 2, not the angle. And then you get, there's your current. And notice that this angle between the EPR and the current is always very close to 90. If there'd be no, let's say sometimes they just give you reactance, they don't give you the resistance, then in this case would just be 3,8 ohms angle 90, eh? Because it would be just reactance. If they say like R is negligible or something like that. Okay. So then you make your angle 90 degrees. But in this case, you calculate the polar. So then the terminal voltage, so we get that, you see, this one here, 1270,17, that is just this minus half times EPR, eh? There it is. There's EPR. Okay. Now you'll see that in this case, when you've got resistance in there, this angle and that angle aren't the same. If you just had reactance in the impedance, those two angles will be the same. But let's put our V terminal now. VT is over here. All right. So we convert that to a line voltage. So why is this angle so important? If they ask you, which they will, synchronizing power. So then what I've done, you can use root 3, VL, IL, cosine of the angle between VL and IL. So then I would use this voltage and this current over here. But okay, I'm using 3 times phase values. It makes no difference. So I'm using the phase voltage, you see. It's star connected, so the current, it doesn't matter. Phase currents equal line current. Then cosine of the difference, between this angle and that angle. That's why you need those angles for the power calculation. All right, that's parallel alternators. As I said, I'm just showing you this slide. This is just, read it in the book. It's just pure theory. There's no big calculations to be done at N5 stage. And this little definition of hunting, know that thing. They ask that a lot. The definition what hunting is. All right. It's not many pages, but I don't want to just read slides here. We've got short time when we're doing part-time. Now, the last part of this AC machines, very important. This is the most widely used motor in the world, the 3-phase induction motor. So we're going to look at how it's constructed, and then you'll see here, stator here. This has got windings on it, makes magnetic field, which gets this rotor going. The amazing thing about this, there's no electrical connection to that rotor. There's nothing. It's the simplest machine. You only put 3-phase in here, which goes to the stator. But I'm going to show you on the slides now. All right. So as I said, no electrical connection, no power supply between stator and rotor. 3-phase here only goes to the stator, and because you have one, what do you have? Magnetic field. And this produces a rotating magnetic field. So that magnetic field is rotating at synchronous speed. And with the induction motor, which makes it a bit different, the rotor speed like this is not equal to the synchronous speed of the magnetic field. So that's the most widely used motor. So the stator and the rotor, the main parts, and the end plates, which house the bearings and protect all the bits and pieces inside. So there's our stator winding. So you see our 3-phase stator winding looks like this. And they wound separately, and then they slide it into that yoke. So the 3 phases are 120 degrees apart. So each one of those phase coils produce its own magnetic field. So if you combine them, it actually comes out to one magnetic field, which is a rotating magnetic field. And it rotates inside, like that, at a speed, synchronous speed, ns. Then you have the rotor. Now the rotor, the simple rotor, is called a squirrel cage rotor. Okay, you strip it down here and we look at this one. Okay, then you see it consists of these rotor bars. So these rotor bars are your conductors. We're used to seeing a wound rotor, with wires wounded. This has just got these rotor bars, and then they are short-circuited at the ends here by means of these end rings. That's it. That's the rotor. And then inside here, it's got all these laminated plates like that, just to increase the magnetic flux. All right, so that's what it looks like. They're skewed rotor bars, and that helps to prevent magnetic noise and make a smoother operation out of this whole construction. So the rotor resistance, you can imagine, is very low. and we can't add additional startup resistors where you have a squirrel cage rotor. So you have quite high inrush currents in the startup. But the good thing about a three-phase induction motor, it is self-starting. The single-phase induction motor, you need those capacitors to get it started. And this one is self-starting. So, but you can't do anything about the large startup currents. So the advantages, the biggest advantage, it's so simple and robust. I mean, there's hardly any parts to this thing. Very low maintenance. You just the bearings. There's no brushes. There's no commutator. No slip rings. So it's smooth and silent operation and long lifespan. It's a workhorse of industry, this motor. Another kind of rotor that you get is a little bit more complicated. It's a slip ring rotor or a wound rotor. So you can see this one has got windings in these slots over here. And then the windings are inside here are connected to these slip rings. So each of these slip rings have a brush on it like that, making contact with it as they're turning. And then these go to external resistors. So this type of rotor, you can have external startup resistors. And you use these, it not only limits the startup current, but it also gives it increased torque at the low end of the speed. So you use it for like cranes and hoists and lifts and things like that. Okay. So it'll look like that. Now, let's go over here. So here's your three-phase supply, three-phase coming in. So you see it's only connected to the stator. This can be star or delta. Doesn't matter however we want to use it. The rotor is always star. Now in this case, we've got this external resistors over here. Hey? So what happens with this R per phase is connected. If you follow this line like that, you see it's in series with the phase impedance of the rotor. So if this is R plus JX over here, this impedance of this one phase, then you simply add this resistance in there and you do your calculation like that. So then once you up to full speed, this thing's got a collar on it which lift the brushes. So it'll lift these brushes off the slip rings. And then what happens is it also short circuits this. Okay. So this short circuiting here equals normal operation. That's how it will. So once it's started up, you don't want these resistors in the circuit all the time. Then the collar lifts the brushes off the slip rings and shorts it out there. So as I said, you get a higher starting torque and your high starting currents are limited. Yeah, you can also change the speed, but these two are the main reasons why you would use such a motor. It's more expensive by far, but sometimes you have to have it. Okay. So the rotating magnetic field, just like with the alternators, the synchronous speed of the rotating magnetic field is given by the frequency of the power supply, typically 50 hertz, times 60 over the number of pole pairs in the rotor. Okay. So you can see once you put the three-phase in there, you get the flux. The flux cuts across the rotor bars. They are short-circuited. Therefore, you get current in these rotor bars. Current in the rotor. And then because of that current, you also get another magnetic field that is coming from the current going through the rotor bars. And then the interaction between these two magnetic fields causes the rotor to start turning. So all the energy that the rotor gets, all of it comes via that magnetic field, which crosses this air gap between the stator and the rotor. And that's it. It's like a transformer. Eh? So the rotor rotates at actual speed NR, where now NR is not equal to NS in this case. Why? Why is an induction motor unable to run at synchronous speed? Because if the rotor is now turning at NR and your magnetic flux is at NSA. So if those two speeds are equal, then there'd be no relative motion between the flux and the rotor bars. Remember, this thing's got the rotor conductors. So Faraday's law says that you'll only induce an EMF in those rotor conductors if the flux is changing. So if there's no relative movement between the two, you're not going to induce any EMF in the rotor bars, then there'll be no current, and then you won't have any secondary magnetic field to produce the force. Eh? So then you won't develop any torque on this rotor. So it can never run at synchronous speed. Now, this difference between rotor speed and synchronous speed is the big, it's known as slip. This little constant for the induction motor. It's the most important thing that you calculate. All right. So the measure of the difference between the synchronous speed of the magnetic field and the actual speed of the rotor is NS minus NR over NS. So can you ever get a zero slip? No. For zero slip, synchronous speed and rotor speed would have to be the same in that equation to give you a zero. Well, we know that's not possible, and we discussed that. So you can get 100% slip, though. Because for 100% slip, NR would have to be zero. If NR is zero, then the slip is just NS over NS equals 1, or percentage slip, 100%. So wherever you see in a question that this word, stand still, or at starting, or at startup, S equals 1. Because you put that, you close the breaker and you apply the three-phase voltage to the stator windings. Now you get that the current in the stator windings, so you get that rotating magnetic flux, but it's going to induce EMF in the rotor conductors. Hey? But it's a tiny fraction of a second just before the rotor starts to turn. Then you have the biggest difference between the rotor speed and the synchronous speed. Once it starts to turn, that difference gets smaller. All right, so energy flow in the induction motor, then you must know this thing. Hey? This thing makes your life easy. Let's just we don't do that. So power in to the whole motor, remember that is rotator input power. So there's a motor in. So that's a power into the stator. No connection to the rotor. You have two types of losses there. Heat losses or copper losses. Eh? So this is heat, I squared R. All right? That's variable. And then you have these constant losses, friction and windage losses, and hysteresis and eddy currents. All right. So power in minus the losses, power losses. Remember, this is all in what true power, hey, in watts. So then your stator losses, then you have stator output power. Yeah. And what does that equal? So it's output power there via the magnetic field equals rotor power. So that's the power input to the rotor. Then you have heat losses in the rotor. So then rotor input power minus these rotor copper losses. Then you get the rotor output power. And quite often they say the power developed is so much and so much. This is specific terminology, eh? If you see this word, power developed, it means rotor output power, not motor output power, eh? Here's the motor output power. Because that the rotor develops that amount of power, but then we have to also subtract mechanical losses. Mechanical losses. So then that's your friction, bearing friction, wind friction, air friction on the fan, for instance. So we subtract those losses. Remember, if they give you, say, the motor output power, and then they want to work out, okay, something simple, just rotor output power. In this direction, you subtract power. In this direction, to get the rotor output power from the motor output power, you have to add power. Hey? So you'd add the losses in the bearings to get from motor output to rotor output. Okay, I think that's a lot we've done tonight here. What I'm going to do is send you these slides, and please read further on, but I'm going to do some of the calculations for this next week as well. But please read through it. This right after this, you'll see that we look at all the formulae. It would help for next week if you just read through those formulae. Okay, so that we can finish off then. All right, guys. There was a lot we did tonight. I don't want to push it now. So I know to concentrate on all this. So if you can, also try and do some of these calculations, but we will still go through the calculations next week. All right. Thank you very much. Cheers.